Hello. Okay. Can you guys also see the screen? Okay. Uh, so we'll start today's session. Uh, Today's session is based on week 4 lectures. So we'll be discussing lecture number 20 to 25. Here are some important links for the TS sessions. You can go through it when I upload the PowerPoint. Here are other important links. So there's a link to our website. There's a link to download our studio. There's a link to GitHub link where all the codes for the course is posted. You can go there and download those codes and run it in your systems. There's also a link to ggplot2, which was taught in this week's lectures. So there's a link to the website where there's also a cheat sheet which will help you make plots better and faster with using ggplot2. So we'll start with the lectures on data visualization. So these are the different kinds of plots and graphs that we were taught about, starting from scatter plot, bar plot, histogram, box plot, heat map, volcano plot, and networks represented as graphs. So what we'll be doing is we'll first take a look at the different plots. Then we'll go to R and learn how to plot those. So scattered plots are sorry. Can you please share all of these here on chat? Don't give us access to the. Oh, okay. Uh, sure, I can do that. 1 second. Uh, of course, you have the links. Uh, okay. Why don't I do one thing? There's a Google Drive link where uh, every week's lectures are uploaded, the PowerPoint presentations that I have. So I'll just share that here in the link. 1 second. Yeah, I'll just share the link to that here. So you can go to this Drive folder. There are all the PowerPoint presentations for all the lectures till now, and also all the codes that we have been using in the problem solving sessions. So yeah, you can go to there and look at these plots. So today's presentation I'll be uploading after the class. So mostly by tomorrow you can take a look at that. So anyways, as I was saying, so a scatter plot is basically used to visualize two numerical variables. So for example, here on the right hand side, we have a scatter plot where we have plotted concentration versus absorbance. So this is taken from a ELISA sample. So we have basically concentration of DNA and what is the corresponding absorbance value. So data in a scatter plot is represented as points generally. This is what we are seeing here. It makes it easy to like visualize and identify if there is some relationship or correlation between these two variables that we are comparing. So for example, just by looking at this graph, we can say maybe there's a log relationship between both these variables. Okay, so now we'll take a look at the code, how to create a scatter plot in R. So all these codes are available in the GitHub link that is mentioned in all of the presentations. The link is also there in the course website. You can go and check there also. So first what we'll do is we'll use a default data set called DNAs. So basically we are creating a variable D where we are storing the data set. So we look at the data set, it looks basically like this. So there are like different runs. So first run, second run, like like basically sets of experiments, and there's the concentration in each of the runs. There are two replicates for the concentration, and the density is basically the absorbance value that we get. Density is based. Yes. So first, what we'll do for plotting this, we'll use the plot function in R. Here we'll provide what we want to plot as the x-axis. So we provide D. D is the data set, dollar concentration. So it will note to choose this column from the D data set. And then on the y-axis, we plot D dollar density. Basically, this one will be plotted on the y-axis. Now, if we just plot this and yeah, just zoom in. Yeah, we just look at the plot. We get a lot of values. So basically, we have our x-axis is concentration and y-axis is density. We have a lot of different values because we have multiple values for concentration here. Okay, so that's one thing. So we'll learn about how to format the plot, and then later we'll just merge all these different values in the concentration column to one value. So first, basically, we are formatting the plot. So basically what we got here is just on the x-axis, it just took the name from the data set. On the y-axis also, it just took the name from the data set, and automatically R set some limits for the x-axis and y-axis and plots your data. So we'll now customize all that. So the plot function takes a lot of different variables. So again, we provided the what we want to plot on the x-axis, what we want to plot on the y-axis. X lab is an argument that defines what should be the label of the x-axis. So whatever you write here will basically come up in place of this D dollar concentration. Okay. And Y label is basically what will come up on the y-axis. So instead of this D dollar density. PCH basically stands for the symbol or the shape of the points that we are making. So currently the points that we have are just basic circles, empty circles. But I think PCH3 is for a plus sign. Color will basically tell R to plot those points in a certain color. So we are using blue color here to plot. Uh, CEX is another argument that basically determines the size of the points. CX dot axis basically determines the label size for the size of these numbers 0, 2, 4, 6 that are on the label. CX dot lab will basically tell you modify the size of the label itself. So 1.5 here means we'll multiply the default value by 1.5. So it will be 1.5 times the default value. Now if I run this, we see as I was telling you. Yeah. So we get concentration on the x-axis because we gave the x lab to be concentration. We get absorbance on the y-axis. PCH is 3, so we get plus marks here instead of empty circles. Color is blue, so all of it is plotted in blue. Cx equal to 2 basically means the size of this is twice of normal. If I were to change it to 1, we can see that the size of the symbols will basically become half of what it was. Right. Then again, the axis and the labels thing modify the size of the axis points, the tick labels here. Basically, these are called tick labels, the numbers that are present on the axis. And then the cx.lab will basically modify the size of the label. Okay. So now we have a lot of different values for each concentration. What we want to do is we want to get the mean absorbance for each concentration and then just plot one value for that concentration. So how we'll do that is we'll use a function in R called aggregate. So basically, we are storing it in another value called another variable called d dot average. D dot average is assigned as aggregate of density tilde concentration. So here is your independent variable concentration. Here is your dependent variable density. D is basically the data set that we have D, the variable, and aggregate function takes like how do you want to aggregate the data. So basically we want to calculate the mean of the data for each of the concentrations. So basically that's why we provided mean here. Now if we run this, we get this table, which has basically like from our data set that we had, the longer data set, we get a smaller data set where for each concentration, we just have a one value for density, which is basically the average value of all of these, like for each concentration across all runs. So here we have the concentrations. Then for run 2 also, we'll have the same concentration, we'll have some density value. It's basically taking the average of all of that. Okay. Then what we do is we plot this now. So we get just one value instead of these multiple values. If we run this, we see that in our plot, we just get one value now for each of the concentrations. Okay. Uh, yeah, but notice that some of these points, for example, the last point here goes beyond the axis limit that we have. So we have 12 here, but our point goes more than 12. So we don't know exactly where the point falls. Again, on the y-axis, the point goes above 1.5, but we don't know what exactly is the value of that point. So for this, what we need to do is we need to adjust the limits of the x and y axis. So we can do that using these arguments in the plot function called xlim and ylim. So basically xlim is equal to, we give it a list 0 to 14. It goes from 0 to 12 now. We wanted to go from 0 to 14. Y limit goes from 0 to 1.5. We wanted to go from 0 to 2. So we just provide these arguments and run the code again. And now we can see that all of our points fall below our axis limits. So this is uh, like how you generally plot your data when you're plotting for any publication or something. So that is basically how we create a scatter plot in R. Uh, let's see how we can do that for like data in another format. So now we'll read another data set, which is called the ELISA data set. So we read it. Basically, its concentration is given, and we have absorbance values, different absorbance values. So basically, the experiment was repeated at these concentrations 4 times. So earlier we had that run variable that was distinguishing the experiment number. Now we just have 4 different columns for absorbance. Okay. So we can, again, to plot a single value for each concentration, we need to get the mean of these absorbance values across the different runs or across the different experiments. So how we get the mean is absorbance.mean is given as row means, and then we give it the data set E. The first part we are giving it as empty because we want to calculate the mean across all rows. And then in the second part, we give it what columns we want to use to calculate the mean. So we want to use the column from 2 to 5. So this is the first column, is the second, third, fourth, fifth. So we'll just be using these 4 columns to calculate the mean across all rows. So we'll run this code and we'll check. Basically, for each of the concentration values, we got a mean. So we have 8 concentrations, so we should have 8 values here, or one for each concentration. Okay. So now note that this is only a vector that contains all the concentration value. This is not a data frame or matrix that contains also the concentration values. So what we'll be doing here in the plot function, we'll take the concentration values from the earlier data set E that we read, and the mean values we'll take from this vector. Then again, we are providing it a X label, Y label. This time we are plotting a different symbol. PCH is 910 instead of 3. Uh, Plot, it's a circle basically. The Yeah, the color is blue and CX, X lim, Y lim is all that I said before. So X limit goes from 0 to 14 and Y limit goes from 0 to 2. Okay. So sometimes what we want to do is instead of a scatter plot, we also want to join the points in the scatter plot so that we can see a trend in the plot. So we can do that in R by basically using this keyword argument type is equal to B. Okay, type is equal to B will plot both the dots and also the lines, like both the points and the lines connecting the points. Note that this is not a smooth line. This basically connects one point to the other directly. Okay. LWD is basically the line width. So if you increase this, the width of the line will change. Instead of the scatter plot plus line plot, if you just wanted a line plot, here instead of type is equal to B, what we would provide is type is equal to L. So this should give us just a line plot where we don't have the values for all the points anymore. Okay. Is this clear to everyone? Okay. So that was all about scatter plots in R. Next, the next type of plot that we looked at was bar plot. So a bar plot basically plots some numeric value on the y-axis and some levels of a different categorical variable on the x-axis. So on the x-axis, we don't have a numerical scale anymore. We have different levels of something. So for example, in this graph here, on the x-axis, we have different stages of the cell cycle. And on the y-axis, we have what is the percentage of cells that are currently in that given stage of cell cycle. Okay. So this is basically the percentage of cells. If we have more number of data points for each of the categories, each of the levels of the categories, we can also plot the mean of the data, such as the mean number of cells across experiments or something. It basically bar plots help us compare some metrics, such as here we are comparing what is the percentage of cell, the value of the percentage of cell across different subgroups of a given variable. So the variable here is the cell cycle stage. Okay. So for bar plots here, what we'll do is we'll read this data set, which is basically flow cytometry data from some experiment. So this is how it looks like. So we have three different treatments. One is untreated, one is drug A, one is drug B. So we have a bunch of cells. The control one is untreated. Then in one set of experiments, we are giving it some drug A, and in another set, we are giving it some drug B. And here we have all the different stages of cell cycle and what percentage of cells are there in this stage for this treatment. This is how the data looks like. Okay. So first what we'll do, we just want to make the bar plot for just the untreated values now. Okay, we don't need to care about these two for now. So what we'll do is we'll just take the first row of the data, which is basically this row, and all of the columns here, 2, 3, 4, 5. So we'll select that from the data and put it in another variable, d dot un for untreated. Then we'll convert it into a matrix. So this is basically how it is. Then we convert it into a matrix before plotting. So this is what we get. Okay. Basically, we just get the first row, the percentages. What we can do to plot a bar plot in R is basically we call the bar plot function. We provided the data, we give it the limits of y-axis, and we give the label of the y-axis. Now, if we plot this is the image that we get. This is the one that we saw before, right? Now, let's say I wanted to see all the three samples. So untreated drug A and drug B, I want to see how does all of that compare, right? So for that, what we need to do is we need to create a matrix first before making a bar plot. So we'll just convert this the whole thing into a matrix. We don't need these three labels now. So we'll just take 2 to 5 rows. So basically 2, 3, 4, 5, these rows, and we'll take, these columns, and we'll take all the rows. We create a matrix called d dot val. So this is how it looks like. Okay. Then we basically plot bar plot. Then we give it the data d dot val, which is a matrix here. I'll just run the code, then I'll explain. It's easier. Yeah. Plotting. Okay, it's plotting, but like the labels untreated drug A and drug B are too big to be shown here. What exactly is happening here? Okay, so ignore this for now. I'll just tell you what the code does. So basically, this is the first argument is the data that we are providing here. The second argument beside is equal to true basically means stack all the three bars side by side. If you put beside equal to first false, then it will stack all the bars vertically. So this will come, then on top of that, this will come, then on top of that, this will come, all three of them. Y lab is basically the label for the y-axis. Legend is basically this thing, which is not properly visible here. So legend is basically, it tells you what color belongs to what variable. Okay. So we provided a list based on the rows that we had. So the first row was untreated, the second one was drug A, and the third one was drug B. Right. So we give legend.text is equal to this list. So it basically sets the legend as these three values. Then we can set some additional legend arguments for legend so that we show it properly. So this is how we do it. Args.legend is equal to list, and then you give it all the options that you want. So X basically gives you where the legend should be. Top right means the legend should come in the top right part of the plot. Then you can put bottom right and all sorts of things. This BTY basically means should R draw box around the legend. So if we put it as Y here instead of N, so it will draw a box. Okay, now it's coming better. Yeah. So BTY means we get a box here. Top right means the legend should be at the top right section. Okay. Yeah. We can also format this plot to change the color and everything. So first, what we do is we create a list of three different colors for these three different treatments. We use light pink, turquoise, and rose. We define this. Then we basically copy the function that was here and we add some argument. So this CX arguments are basically to increase the size of the text and the size of the text. Access names is basically this legend and label is the label. Then here is the color argument. So COL is equal to my call. So this my call is the vector that we created containing three different colors. We'll just provide that to the color variable. And what it will do is, for each of these classes, it will assign one color. So untreated will be light pink, drug A will be the second color, and drug B will be the third color. If I run this now, the colors also change. Note that colors will change everywhere in the graph and also in the legend automatically. Okay. Is this clear? Does anyone have any issues till now? Okay. Let's just clear all this. So the next plot that we talked about was a histogram. So basically, a histogram is used to visualize a large amount of data if you want to know what the distribution of the data is. So for example, here we have an example histogram of like distribution of salaries of employee in some corporation. So what we have here on the x-axis is the salary, a range of salary going from 0 to 200,000. And on the y-axis, we have the frequency or the number of employees that are in a given salary band. So each of these boxes is a band. So this is from 0 to, let's say, 25 or 20 or something. This from 20 to 40 and 40 to 60 and so on. In each of the band, the height represents how many number of employees or what is the frequency of that band occurring. Okay, so histogram is basically useful when you have a large number of data points and you want to visualize what the distribution of that data point looks like, variable looks like. So let's say we have a data set here where we have 10 students of the class. We have their roll numbers and what marks they scored in a test. So out of 50. So basically this is what roll number 1 scored, roll number 2, 3 scored 22, 4 scored 27 and so on. So to create a histogram, first what we need to do is we need to bin the data into different bins. So basically, we want to plot this distribution of the marks column. So we'll bin the mark column. Okay. So we'll put the range of marks from 0 to 10, 11 to 20, 21 to 30, 31 to 40, 41 to 50. The size of each bin should be the same. And we put different bins starting from 0 till 50, which is the highest that people can get. Next, what we do is we just count the number of students that fall in the first bin. So basically, there's just one person with 6. So the count of students here will be 1. 11 to 20, we have 13, 15, and 20. So 3 people. 21 to 30, we have 22, 27, and 26, 3 people. 31 to 40, we have 35, 33, 2 people. 41 to 50, we have just one person, 50. Right. Next, what we do is we basically plot it. So for plotting, on the x-axis, we'll take the marks. 0 to 10 will be one bin, 10 to 20 will be another, 20 to 30 will be the next, and so on till 50. And frequency is basically the number of students that fall into the bin. So here the frequency is 3, 3, here it's 2, and in both of these cases, it's 1. Okay, is that clear? Okay, so now we'll take a look at how we can plot a histogram in R. So basically, we are reading the flow cytometry data again. And if we take a look at the data, so this is how the data looks like. So these different columns are different measurements. And in total, we have 20,000 samples. So each row represents a sample. Right. So let's say we are only interested in this column, FL2H, that is some kind of measurement. We want to see what is the distribution of that variable across all the samples. So what we'll do is we'll use the hist function in R. So hist, and then we give it the column that we want. So f $fl2 dot h. Fl2 dot h is the name of the column. F is the name of the data set that we have created. So if we plot this, we get a histogram. This is basically the bins, different bins, and what is the frequency of samples in each bin. So basically, we see that there's one peak here near 200. So most of the samples have a value somewhere around 200. Right. Again, what we do here is we adjust the x limit and the y limit so that the graph looks better. Then we put the labels for the x-axis and the y-axis. You notice this name here, histogram of f$fl2.h. So this is defined by the main argument here. So main basically gives the name of the graph. So if we set it to an empty string, this name should disappear. Okay, now we just run this. We see that the name disappears. And this LAS thing is basically the orientation of the x-axis, like the rotation. If we put it as 1, it comes as horizontal. That's the way we want. If we put it as 2, it will be, you just saw, it will be rotated like this. Right. Yeah. So in a histogram, one of the important things that you need to figure out is how to bin your data. Okay. So generally, if you bin your data differently, like, yeah, here we have some certain number of bins. If we change the number of bins, just remove the, yeah. 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 So now you see the histogram looks very different now. If I change the number of bins again, you see that the distribution looks very different. Now we have a peak near 0 also. Like there's some value that's high here also. And maybe we have a small peak here or something. So the distribution that you see will depend on the number of bins that you have. So how do we find the optimal number of bins? R generally has a lot of different functions that can help you figure out what should be the optimal number of bins. So if you go to the help section and look for histogram, you see the arguments. So basically break is the argument which uh, tells the R, like which tells R where to break the uh, x-axis or like how many bins to make. Okay, so breaks is a function. You can supply a vector here so that if you give a vector, it will basically use that vector to mark the endpoints of the different bins. If you give it a number, it will give you that many bins. So if I gave it, when I gave it 100, this is 100 bins we get for the data. If I give 10, we get 10 bins for the data and so on. And there are other functions also. There are other like basically statistical methods to estimate what should be the optimal number of bins for your data. So one of them is called the Friedman-Diaconis rule. So R has implementations for this and other different statistical methods also to estimate the number of bins. So what you do is you give breaks is equal to and you write just FT. So it will now use this method to estimate what should be the optimal number of bins of the data. Okay, you don't need to worry about what bin size or how many bins you want in your data. Okay, so now that we have a distribution, we want to see where the mean and the median of the distribution lie. Okay, so for that, what we'll do here is we'll use this AB line, which is a function in R, which basically creates a vertical line here. So we give it the argument v is equal to mean. So basically, we are plotting the mean in the first time, in the first line here. We are giving it the color blue and line width is basically 2. If we run this, we see that we get a bar here which represents what is the mean of our data. The same thing we can do for median. So AB line, here we give median of the column, line width, and the color is red. So basically, we get a red line on the median of the data now. Okay. So another thing is on the y-axis, here we have counts, but in some cases we might need density. Okay. So I'll just run this. So this is basically a histogram where we have plotted the density. If you give the frequency is equal to false option here, it will give you the density. If you put it back as true, you run it, it gives you the frequency or the count. Okay. If you give frequency is equal to false, it plots the density. So the area under all of it should, the sum of area, the area under all of these bars will now be 1. This is basically a probability density of the whole like variable, right? We can change this frequency count to percentage so that it's easier for us to understand. So how we'll do that is, so first we'll create another variable h where we'll store a histogram object. Okay. Here we are providing it plot equal to false. So basically it will not plot anything. So I'm clearing it. If I run this code, it will basically create a histogram, but it won't plot anything. Now we'll take a look at H. So what it looks like. H basically is a description of the whole histogram. So we have breaks where all the breaks are there for the bins. Count is basically what all are the counts. Density is the density for each of the bins. And name is there and so on. Okay. So what we want to do is we want to convert the density to percentage. So what we do is we take the counts from the uh, counts that are determined here by R. We take the counts, we multiply it by 100 and we divide it by sum of all the counts. Basically, we are taking in each bin the number of counts, like the number of occurrences, the frequency, divided by total number of observations that we have, and we are multiplying it by 100. So that is basically giving us a percentage. Now we store this percentage as H dollar density. Note that the density value here is very low, the original one. Now if we run this code and we check it again, the value of density has changed. Now it has been converted into a percentage. Okay, so now we'll basically plot it again. So now we are just plotting H. We created a histogram object. We'll use the plot function to plot it. So plot H, frequency we are giving false so that we just plot the whatever is there in the density, which is now the percentage. We give it the limits for x-axis, y-axis. We give it the labels for x-axis, y-axis, and we give it a color. So now when we plot this is how the histogram looks like. On the y-axis, we have the percentages of cell instead of the counts or the density. And on the x-axis, we have the variable we wanted to see. Right. Okay. There's a question. Could you please share the CSV files used in the instruction videos? Okay, so I gave you a link for the drive, no? Everything is uploaded there. So there's a link in the chat box. Uh, I'll highlight it again. Yeah, you can go to that link. Uh, there's a folder called week 3, which contains all the materials and CSV files for week 3. For week 4, I'll upload it today. So by tomorrow, you can see all of the code and everything. Okay. Yeah. So I'll just clear all of it. Yeah, so that is how you create a histogram in R. Next, what we'll look at is box plot. So histogram lets us visualize one distribution at a time for one variable, distribution of one variable. Using a box plot lets us summarize and visualize multiple distributions, like multiple variables at the same time. So for example, in this graph here, we have different types of insect sprays, and insect count is basically the number of insects or the different kinds of insects that they are effective against or something. So here we can see a distribution of the whole, like for A column, what is the distribution, for B column, what is the distribution. So like for spray type B, what is the distribution, for spray type C, what is the distribution, and so on. This is like a box plot is typically helpful when we are comparing the distribution of numerical variables between multiple groups. So here we have multiple groups. All of these are numeric variables, and we are comparing the distributions. A box plot offers us a lot of information at a glance, including the median, the quartiles, and the outliers. So we'll talk about it in depth now. So basically, this is basically a box plot rotated horizontally. So here what we have in vertical, we have just put it in horizontal here. So the middle line that we have, the black line here, is basically the median of the whole data. Okay. The box is drawn. The box starts from the first quartile of the data, and the box ends at the third quartile. So first quartile is basically after 25% of the data is there. So this is like below this 25% of the data is there. Above this 75% of the data is there. Quartile 3 is basically below this 75% of the data is there. Above this 25% of the data is there. So here, this line here, so this is basically the median. This is the first quartile. This is the second quartile. And this whole thing is called the interquartile range, IQR. So IQR is basically Q3 minus Q1, right? Q3 minus Q1. Then we have these whiskers. Okay. The lower whisker where it ends is called the minimum, and the upper one is called the maximum. So these are not the minimum and the maximum of the distribution or the whole data set. So this is the minimum is defined as quartile 1 minus 1.5 times the interquartile range, and the maximum is defined as quartile 3 plus 1.5 times the interquartile range. Okay. So basically here what we are doing, we have this interquartile range. We'll multiply it by 1.5. Then we'll plot, like we'll add it to the Q3 here. Q3 we have here, Q1 we have here. So this point should be Q1 minus 1.5 times IQR. And this one should be Q3 plus 1.5 times IQR. But you would say this does not look like 1.5 times, right? So basically what we do is we find the number here for the maximum and the minimum, and we check what actual data point is there, which is equal to or less than this, and then we end it there. So basically this is like the minimum data that is there. Either it's the minimum or it's this value. So either it's the maximum or it's this value. Okay. And the dots that you see here, the dots that we get outside of these whiskers are called outliers. So these are basically data that are like at the far ends of the distribution. Right. So if we plot a box plot for a standard normal distribution, what we see is that 50% of the data, 50% of the data in a standard normal distribution will fall between, will fall in the interquartile range. So will fall in the box, and 0.7% of the data will remain as outliers. The rest of it will be covered if you are plotting a box plot for a standard normal distribution. Okay. So now we'll take a look at how we plot box plots in R. So we'll use a inbuilt data set called insect space. So basically, it has the count of insects and what is the spray type, right? So what we, for creating a box plot here, what we need to do is we need to write count tilde spray. Okay, so spray here will be plotted on the x-axis. Count here will be plotted on the y-axis. D is the data that we just assigned, data frame data variable, and box plot is the function to make the box plot. We'll run this and we see that we get a box plot where spray is on the x-axis and count is on the y-axis. Okay, so R automatically takes all the different types of spray into account and creates different box plots for all of them. You don't need to specify that anywhere here when you're creating a box plot using this function. Okay, so we can also format the box plot to make it look better. So we can provide a X label instead of spray. Will write type of spray. The Y label will change to insect count. We'll increase the size of the label and the axis text. Okay. The Y limit will extend to 30 because this line falls after 25. Where width basically gives variable width to these columns based on the number of data points that they have. So for example, if the B column here had more data frames, the width of this column would have been more. But in our data set, we have equal number for all of them. So all of these boxes have equal width. Okay. Just run this code. Huh. So out PCH is basically what symbol you want to use for outliers. 19 is basically a filled circle. And out call is basically the color. So if we change from red to blue, it will show outliers in blue. Right. If we change this to 3, it will show it as plus. Is this clear to everyone? Does anyone have any doubts regarding this? Okay, we'll just clear all this. Yeah. So next we were taught about heat map. So heat map is basically a two-dimensional visualization of a matrix. So basically we have certain columns here and certain rows here, and the color in each of these cells, in the intersecting cells for each column and each row, will tell us what is the value there. So if we have a large amount of data in a matrix form and we want to visually look at it and quickly figure out if like some values are very high, some values are very low, if like some rows have similar values or some columns have similar values, then we can use a heat map. So here in the heat map, the lighter color represents that the value here is very low and the darker color represents that the value here is very high. Okay. So now we'll take a look at how we can create heat maps using R. So we'll read a data frame here. So this is basically a data frame. We have, I think, uh, certain genes and certain different individuals on the rows and different genes on the columns, which basically, yeah, tells us how much this gene is expressed and gene expression basically. So in different individuals, what is the uh, gene expression? Sorry, I'll just copy and paste the link again. Uh, okay, yeah. Huh. So what we are doing now here is we are modifying the data frame slightly. So we are creating a matrix out of it. Okay. we are basically changing the data frame into a matrix. Row names dot force equal to true basically keeps the row names here. If I were to put it as false and run it again, you'll see that the row names are changed. But because we are doing a heat map, we want to know what are there in the row names. We put it as true and we run. Okay, now our data is in a matrix form. So to create a heat map, I'll just run the code and then explain. Basically, we are using the first 10 rows and all the columns from the data set. We are basically using only the first 10 rows. Otherwise, it might be too difficult to visualize because there are 12,000 rows. Okay, we take the first 10 rows and we take the first 10 rows and all the columns that are there. We have around, 47 columns or something. Yeah, and this basically, these two variables, row v and col v, basically tell R not to produce a dendrogram or a cluster. So if I remove this and plot it again, you see that R plots a cluster or a dendrogram. So a cluster is basically, it means that these two genes are similar, like genes are expressed similarly across different people or something. Okay. And if we remove this, we'll get another cluster for the columns. Okay. So columns were like different samples or different uh, cells or individuals or something. So this basically clusters the individuals. Okay, we'll run it again without any of this. This is how it looks like. So note that, let's say here, yeah, it's difficult, but like basically the darker values have higher, darker cells here have higher values and the lighter cells have lower values. Okay. So if we remove both these arguments, we can get dendrograms in the heat map, which basically cluster our rows and columns based on how similar they are. Okay. So, but like the image that we are getting here currently, it tells that these two rows are similar, but they're like these two rows are clustered together. So these two rows are similar. Yeah, these two rows expression should be similar, but we don't see that visually, right? So what we need to do is we basically need to scale the columns. So these columns might have different means and standard deviation. What we need to do is we need to scale the column so that the values across all the columns are uniformly represented. Okay. So we just provide a argument here to the heat map function called scale equal to column, which basically scales the columns. And now we see that once we have scaled the columns, we can visualize that, okay, these two are expressed similarly, which is higher than the genes here, right? Then generally when we are doing this, we want to find out which genes are uh, expressed similarly across individuals. We don't want to have a cluster of individuals. So we don't need this column thing. We just need the row thing. So we'll again use the argument here, col v is equal to NA to remove this. And we'll scale it by column. And we'll plot the heat map to get the final heat map, which basically tells us what is the gene expression for these different genes across individuals. And it also clusters the genes together based on their expression values across individuals. Okay, that's it for heat maps. Does anyone have any issues with this? Okay. The next type of plot that we looked at is called a volcano plot. A volcano plot is basically a special type of a scatter plot, which is used to quickly identify changes in large data sets. Okay. Generally, we use it in biological data sets such as in genomics, proteomics, or other such experiments, where we want to see. So on the x-axis, we have log2 fold change, which is basically the change in gene expression. If it is greater than 1, Basically, that means since we are taking log of 2, if the value is greater than 1, it means that the gene expression has increased to at least twice of the value that should normally happen, right? So twice is generally thought of as biologically significant. And if we get something that is lower than -1, so basically it means the gene has been downregulated. So the gene expression has been halved. Okay. And here on the y-axis, we have uh, significance. So basically p values. And on the bar here, we have what is the statistically significant, which is basically the p value for 0.05. So here we plot it on a log scale so that it's easier to visualize. And anything that falls below this line on the x-axis and above this line on the y-axis is basically statistically significantly different and biologically relevant and down-regulated genes. These things are statistically significant, biologically relevant, and upregulated genes. Anything that falls in between here, anything that falls above this horizontal line is basically statistically significant. But these points here are not biologically relevant because the change in expression is not as much as it should be. Right. So, yeah. So basically, I'll go through it again. Gene expression is often represented as a fold change. So fold change is basically we have some untreated sample, then we put some, let's say, substrate or some chemical, and then we measure the gene expression again. Then we get a value of gene expression in the treated sample. So the ratio of treated to untreated is basically called the fold change value. Okay. If fold change is greater than 1, that is this part, the reading in the treated is greater than the reading in the untreated, it means that the gene is upregulated. If the reading in treated is less than the reading in untreated, then this fold change value will be less than 1, and that means the gene is downregulated. Okay. So when we log transform this thing, so if we have a value greater than 1, then the log transform of it. So basically, if we take a log of it, it becomes positive. And if we take the value here and we take the log of it, it becomes like value which is less than 1. If we take the log of it, then the value becomes negative. So it's easier for us to visualize. That's why we use a log transformation so that instead of this greater than 1, less than 1 fraction and like some number, we have a positive and a negative scale. Okay. We generally use log base 2 because uh, as I told you, if it's at least if the expression is halved or if the expression is doubled, then we say that the change is biologically significant. That's why we are taking a log base 2. So basically, if we get a value greater than 1 in log base 2, it means that the gene is overexpressed at least twice. If we get a value less than -1, then that means the expression of the gene has been halved. Okay. So in this script to make a volcano plot, we'll be using the ggplot library. We'll talk about it shortly. Now we'll just use it and I'll tell you basically what we are doing. Then later we'll get into depth of how to use ggplot and all. So first thing we need to do is import the library. But before that, you need to make sure that you have the package installed, ggplot2. So for that, what you need to do is go to Tools, Install Packages, and then type here ggplot2 and just press install. So I already have it installed, so I don't want to install it again. Then we run this code library ggplot, which basically loads the ggplot library to and makes it available for us here in this workspace. So we read data for the volcano plot. This is how the data looks like. So we have different gene names. We have the log2 fold change, and they have done some experiment to determine if it's statistically significant or not. So we have p values also for each of these genes. We have the log2 fold change values, and we have the p values. Okay. So here what we are doing, we are creating a plot object basically assigning it using ggplot. Yeah, Archana. Uh, yeah, you can ask if you have any doubt. I can't hear you. Are you speaking? Is it the same thing that you asked in the chat? Why can't we use fold change and keep a line between -2 and 2? Okay. I can't hear you. Can you speak louder? It's the same question, no? That you asked in the chat. Okay, I'll just explain. So basically, what we have fold change values are basically value in treated divided by value in untreated, right? So if we have values greater than 1, which means the treated is more than the untreated. The value that we get, expression that we get in treated is greater than the expression that we get in untreated. If we have less than 1, then it's the opposite. For biological significance, we say that this should be at least twice as more expressed or half as much expressed for it to be biologically relevant. Okay. So for twice, what we need to do is fold change needs to be greater than 2 for it to be biologically relevant if it is upregulated. However, if the gene is downregulated, then the fold change value needs to be less than 0.5 and not less than -2 because we are taking a ratio here. And both of these things are positive quantities. So we don't have any negative numbers. Okay. So if we were to just plot the fold change here on the x-axis, okay. So basically we'll get 1 second. Okay, what is this image? This looks like half of a volcano plot. The right hand side here. I can't hear you. Can you type what you're trying to say? I think you are muted. Can you unmute? Can you try speaking now? Hello? I still can't hear you. Can you type it here in the chat box? Hello, Archana? Okay. Yeah, you can type. So basically what I was telling here is that the fold change value will always be positive. It won't ever be negative, and it will vary from like 0 to infinity. Okay. And here we can set two lines, one at 0.5 and one at 2. But then it's not really symmetric, right? One will be here. One basically means there is no change in gene expression. Okay. And this line here, which is basically half of it, this is much closer to it than this line here. So it's like slightly imbalanced and all. So that's why it's better for visualization if we take a log of it. See, again, in this plot, it's very difficult to visualize. Yeah, I understand that. You have not taken the log here, but like difficult to like see what exactly is happening. This plot that we get here using a volcano plot is much more easier to analyze and it is much more symmetric. Okay, fold change values can be negative also. But again, like this imbalance will still be there. Huh. So you see the last graph, you're using the same data set, right? That I have been using. Huh. So you see the genes that you're getting there on the right hand side, how clustered they are. If you do a log transform, I think that cluster thing will go away and your points will be much more easier to visualize. You can try taking the log for both of these, the p-value and the fold change, and plot it again. Then you can also share it here on the chat so that everyone can see. So it just makes the plot look better and all the points are very clustered here. It won't be very clustered when you take the log values. If you still have any more doubts, you can ask on the discussion forum once. Sir might reply to it. Like why exactly uh, we take this 2 and log 2 and not something else. But this is the idea that I have. Okay. Yeah, so we'll continue. As I was saying before, we have a data set here, volcano.data. So the gene symbols, we have the different genes, we have the log2 fold change, and we have the p-values, right? So here using ggplot, what we are doing is we are creating a plot. Yes, the second plot looks much better, right? Yeah, it's basically easier to visualize this way, is what I feel. We should ask it in the discussion forum. I think uh, they will like, yeah, they can probably be able to help you better with regard to this. Uh, if you share your code, I can check if and the data set, we can try plotting to see why there are no downregulated genes here showing up here. Can we do that at the end of the class? Yeah, yeah. At the end of the class, I'll like you can share the data set that you are using. I'll try and use that data set to make the volcano plot. Is that okay? Cool. So here what we are doing, we are using ggplot. So ggplot, first you need to give it what data you are going to use. So data is equal to v dot data that we read here. AES is basically the aesthetics which tells ggplot what to plot on the x-axis and what to plot on the y-axis. Okay, so we have the p-value here and we have log2 fold change here. On the x-axis, we are giving log2 fold change. On the y-axis, we are taking negative log of the p-value. Okay, then this third line, then we write a plus to add another function basically on top of it, another thing. So this is called geom underscore point, which basically tells ggplot to plot it as points. So if we put geom underscore line, it will make a line plot. If we put geom underscore bar, it will make a bar plot and so on. So we do this. It does not basically show a plot because we have just stored it to a variable. So when we call that variable, we get a plot, right? So this is the normal plot of log2 fold change versus minus log 10 of the p-values that we got from the dataset here, right? So for biological relevance, what I told was the fold change should be either twice or half, right? So for in terms of log2 values, it will be either greater than 1 on the x-axis or less than minus 1, right? So we add a vertical line for 1 and we add another vertical line for minus 1 here so that we visualize those lines on the graph. So what we are doing here, plot 2 is basically plot 1. So this plot object that we created here plus geom v line, which is basically a vertical line. We are saying the x-intercept is 1 and minus 1. So we are drawing two vertical lines and color is blue. Then we are adding another, note that there's a plus symbol here. We are adding another horizontal line for the p-value. So cutoff for p-value we are taking as 0.05. So we want the horizontal line, geom underscore h line, to be at this value of y. So y-intercept value should be minus log 10 of 0.05. And the color we are giving is blue. So again, we plot this and now we see that we have three lines. We have two vertical lines for biological significance. So minus 1 is basically when the gene expression is halved, plus 1 is basically when the gene expression is doubled. And we have one horizontal line which indicates the p-value of 0.05, which is our level of significance here. Okay. So now what we want to do is we want to color code these genes that are both biologically and statistically significant. So these things on the right upper corner and these things on the left upper corner. So for that, we need to create another column in the data set so that we keep track of which genes are upregulated, which genes are downregulated. So we create another column here, v dot data diff expressed is no. So when we do this, we see we have created another column here, diff expressed, where all the values are initially no. Okay, all of these values will be no. Then what we are doing here is we are, for that column, diff expressed, we are seeing if the, in the row, if the log2 fold change is greater than or equal to 1, and the p-value of the row is less than equal to 0.05, we know that it falls on the right upper corner here. So we denote it as up. So basically these genes are upregulated genes. Now if we run this code, we see that wherever we have a p-value less than 0.05 and we have upregulation greater than 1, so basically log2 fold change greater than 1, the no changes to up. Similarly, for downregulated genes, we put the condition p-value is less than 0.05 and log2 fold changes less than equal to minus 1. We run this and now we see we have a data set where we know which genes are downregulated, which genes are upregulated, and no basically means that these are not biologically relevant for us, right? So we'll create another plot. Show the code. Yeah. Basically, we are using ggplot. We are giving it the data. We are telling in AES here what is the x-axis, what is the y-axis. Color we are also giving here. Color basically is we are using this column diff express to color the points. So if the point is down, it will get one color. If the point is no, it will get another color. And if the point is up, it will get another color. Okay. Then we write geom underscore point because we want point scatter plot. Theme minimal basically modifies these background color and the grid lines and all that we have. And scale color manual basically gives the colors that we want to use for the different things. Right. So red we want to use for uh, the first one, black we want to use for the middle one, and green we want to use for the upregulated ones. Right. Then again, this V line and H line is basically these lines of significance. Just run this. Yeah. And we see that all the down variables are coded as red. The upregulated ones are coded as green, and the rest ones are coded as black. So these are the three colors that we provided here. Okay. So we also want to add labels to these genes so that we know which genes are upregulated and which genes are downregulated. Right. So for that, we'll create another column in the data set called G label, which is basically empty for now. So G label, we put NA. Okay. You say wherever in rows, if the differential express like this column is not equal to no. So wherever this column has a value that is not no, wherever this is down or up, what we do is we select the gene symbol, and using that same argument here, we copy the gene symbol into the G label. If the this variable diff express is not equal to no. If I run this, so note that here all the values are NA now. If I run this and we view the data, wherever the diff express value here is not no, it's down or up, then we get the gene symbol from here and we copy it here. So basically we are just getting the labels of the different genes. Okay. Now we want to show those labels. So here again in ggplot, we are adding in the aesthetics AES bracket, we are adding another thing, label is equal to G label. So we are giving it the column where we have all the labels. Okay. And at the end, we are writing geom underscore text. So basically it will put all the text, like all the labels. If you run this, we see that we only get the labels for the genes that are upregulated or downregulated and not the other things, because we don't have labels for the other things in the G label column, right? Okay. Is that clear to everyone? Okay. Hmm. So basically to create the volcano plot, we used a library called ggplot. Ggplot is basically the one of the most used libraries in R for plotting. So the GG in ggplot2 stands for grammar of graphics. So basically a plot or a graphics is made using multiple components, grammatical components connected together in ggplot. That is the basic uh, logic behind making plots using ggplot. So there are three major grammatical elements that we need to define for each plot, which tells ggplot what to plot and all. So basically the data we have what to plot. We provide it a data set. Geometry basically tells ggplot what kind of plot to make, whether to make a scatter plot or a line plot or a bar plot and so on. Aesthetics basically tells ggplot where should we plot what. Okay, what should be the x-axis, what should be the y-axis, and so on. There are other grammatical elements such as statistics, which basically helps us transform the data using some statistics. Coordinates, which basically tells which coordinate system to use, and themes, which is basically all the other things apart from data and plotting. So basically the background and the grid lines and all things like that. So we'll be discussing about these major components and also statistic and themes in detail over here. So yeah, to basically run the script, we need both these libraries, ggplot and reshape. So again, install using tool, install that packages reshape 2. You can go and install it. Then what we do is we load those libraries. We are reading some data here, D1, which is basically first column, we have the concentration. Then we have untreated some values and treated after treatment, what is the value? Okay. So now we just want to create a scatter plot for this. So we want concentration on the x-axis and these two variables on the y-axis. We'll step by step, we'll do that using ggplot. So first, if you just run ggplot like this without anything, it basically creates a gray thing with nothing plotted because we didn't provide anything. Next, we provide it with the data. So data is D1 here, we provide the data. But again, the plot we get is basically blank because we didn't tell it what to plot and how to plot, right? So now we are providing the aesthetics. So AES, and in bracket, we provide that X is equal to concentration. So the name of the column. So on the x-axis, we want concentration is what we are telling ggplot. And the data is D1. If we run this, we see that we have a x-axis now, which is concentration, but nothing else. Again, we provide a y-axis treated. Right. Now we have a x-axis and a y-axis, but still we don't see the points because we need to add this line, which is basically the geometry, which tells ggplot what kind of plot to make. So we are using geom.point. So basically it will make a scatter plot. And note that this data and aesthetics are defined inside ggplot. Then we are adding a plus and we are giving it the function geom_point. Right. This plus needs to be after this line. Right. And we can add multiple elements like this. Add multiple sets of grammars using ggplot like this. So if we plot this now, we get the scatter plot, where on the x-axis we have concentration, on the y-axis we have values from the treated column. Here, right? So like we did before, we want to we don't want to write all of this again and again. So we can basically create a variable and then build upon it. So we assign this whole plot to a variable p1. If we plot p1, we basically get the same thing. Now we want to add a line on top of that plot. So basically we just write p1 plus we write geom_line. It will basically add a line to the plot. Now if we plot p2, we see that we have the dots and again we have the line also passing through it, just connecting all these dots in a straight line, right? So since we want to plot both the treated and untreated ones, we'll be using a function called melt from the reshape package, which basically modifies our data frame. So we are creating another data frame. Okay, D2 here. We'll see what it looks like. Now we have basically concentration, another column called variable, and another column called value. Here we just had all the values for untreated in one column, for treated in one column. We are changing it so that we have a variable here, which is named as treated or untreated. And then we have all the values here. So basically, how do we do that? We write the function melt. We give it the data set that we want to change. id.vars is the thing that won't change. That is the concentration. Right, that's basically the ID. Measured or vars is basically what we want to combine. Treated and untreated, here in data 1, we have separate. We want to combine into one column. So that is what it is doing here. So measured dot vars, we give treated and untreated. Now if we write this, yeah, we ran this. So basically the column names that we have here are variable and value, which are not uh, quite explainable. So what we'll do is we'll change the column names to concentration. What is the sample? Is it treated or untreated? And then we put the third one as absorbance. Okay, run this, and we see again we have changed the column names to sample and absorbance. So basically we assign this column names D2 is equal to some list, right? Now we want to create a scatter plot. Okay, so we have P3 is ggplot. We are providing the data set D2. Aesthetics, x-axis we want the concentration, y-axis we want the absorbance. Okay, so this D2 data set has concentration, absorbance, and color is basically what color we want, like how do we want to color the plot. So we want to color it according to the sample. So treated will get one color, untreated will get another color. And we want it to be a scatter plot, so we are writing geom_point. We run this, we see that we are getting a scatter plot with two different colors. Treated is one color and untreated is one color. Great. On top of this plot that we created just now, we can add a line so that it makes like shows us the trend. So we can add a smooth line by using a function called geom_smooth. Right. Now if we run this, we see that we are basically R is fitting a line to the data. Right. It's not connecting the dots. It's basically fitting a data, smooth line on top of the data. This SC basically tells our ggplot not to plot the confidence interval. Right. If we put it as true here, we'll also get some variance or confidence interval kind of thing. Basically the error. We don't want that. And the span variable here will tell ggplot how much to fit the line or how much to smoothen the line. So for example, if I put it as 0.5, know that the line is not that smooth. If I put it as some higher value, the line will be much smoother. Okay. Yeah. Now we are adding on to that plot. We write P4 plus labs is basically used to define labels. So labs X is equal to concentration. We are changing the X label to concentration and the Y label to absorbance. And here color, we have written just sample S is small. We want samples as capital. So we write color is equal to samples. So basically, if we plot this, see that we should have a better x-axis, y-axis, and the legend, the name changes here. Right. To fix the limit of the y-axis, since this value is going above 3, we use P5 is basically what we defined till now. P5 plus y lim 0 to 4. Straightforward. We plot this, we change the limit. Theme basically defines, as I told you before, all the non-data ink. So basically the grid lines, the background and everything. If you want to change the theme, we write plus theme_classic. You can also create your own themes and all using ggplot. So that's something you can look up in ggplot. So if we run this, it's quite simple. We got rid of the all background color and grid lines and all. And now the plot looks much better. Right. Finally, what we'll do here is whatever we have done till now by adding to the plot, first plot, what we'll do now, we'll just write everything together. So basically we have ggplot, data is D2, aesthetics maybe are telling X is concentration, Y is absorbance, and color it according to the sample that we have, treated or untreated. Geom point is basically plot points. Size basically tells you what size the point should be. Geom smooth, basically if it's a smooth line, SC means don't put the standard error standard error thing. And span basically tells you how smooth it's going to be. Labs will basically define the label, the x-axis label, y-axis label, the color label. Y limit will be basically change the Y limit of the plot, and theme classic basically changes the theme. Now if we plot this, you see that the only difference is that the point size is bigger because we have provided size is equal to 3 here. And we get the final plot. Is that clear? Does anyone have any issues with this? Okay, great. So then we'll also look at how we can use the statistics layer in ggplot. Okay, so basically we call the library, we read a data frame. So this flow cytometric data again. So like, yeah, we have basically these different variables and we have different samples here on the rows, 20,000 samples we have. We want to basically create a histogram of FL2H like before, right? So now we'll be using ggplot to do that. So fscs.plot1 is the variable that we are creating to store the plot. So ggplot, fscs is the data set that we just read. Aesthetics may we write X should be this column, fl2.h, which is there in this data frame, right? And we put a plus sign, we write geom underscore histogram. So ggplot knows that it needs to plot a histogram. So that's what it does, basically, right? If you want to change the width of the bins in histogram, okay, so you can use bin width argument here, bin width equal to 5, 10, or whatever. Note that when we are calling this histogram function inherently, we are just providing it the values, right, for each sample. ggplot in the like behind the screens, it's calculating some statistics to get at the distribution, right? So the statistics here is like happening inherently inside it. We are not explicitly doing any statistics to make the plot. That's one thing to note. Right. So now we are changing the bin width. So yeah, we get a bin width of 5. Now, what we want to do is we want to make it prettier. So basically what we'll do here is, again, we have FSC as a data set. Aesthetics, we have x-axis is this. We have bin width of 5 we are providing. Labs is basically the label. So x-axis label is fl2 -h and y-axis label is count C capital. Limit y-axis we put it from 0 to 400. Theme we change to classic. Then here we are modifying elements from the theme like uh, for ourselves, basically. Like, so theme classic basically has some elements that are defined by ggplot that it will use, but we can also modify the theme further by using this theme function. So what we are doing here is access.text. We are basically changing the text in the access. We are changing the element size, like basically the text size to 12, and the font family, basically we are changing the font to sans. We are doing the same for text and title. Text is basically this, and title is basically title of the access. If we run this, we see that the access labels have also grown bigger. The size has changed. The font has changed. The access title also size and font have changed. We have the x-axis label, y-axis label, and we have our histogram. Right. We did not need to call any statistics. We just needed to call geom underscore histogram, and ggplot calculated all the statistics and made the plot behind the screen without us ever having to bin the data and everything. Right. So yeah. Next, we learn how we can call statistics within a geom. Okay, so basically we'll read the insect sprays data set again, and we'll create a box plot. So this is how the insect sprays data set looks like. So we have two columns, count and spray. Spray is basically different types of spray, and count is the count. Right. We're making a box plot using ggplot. So D is the data we are providing. D is the data that we just loaded. On the x-axis, we want spray. On the y-axis, we want count. So spray and count. Right. Color, we want to color the data according to the spray. Right. So if according to different kinds of spray, the data will be colored differently. Then we write geom underscore box plot. Outlier color basically is the color of the outlier. Outlier shape is again that PCH thing. What should be the shape of the outlier? Size is basically what is the size of the outlier. Show legend equal to false we are putting here because we don't want a legend. Okay, we'll make the plot and I'll explain further. Yeah. So basically show legend we have put as false because we don't want the legend. If I put it as true, it's basically redundant data. What we are getting is what is the color of each spray. But anyways, we have all the sprays and colors in different categories here in different uh, vertical lines. So we don't need that legend. We'll put it as false. Right. We are setting the labels, X label, Y label. We are setting the Y limit. Again, we are setting the theme and we are modifying the elements of the theme to make the like axis text and axis title bigger. Right. Again, here the statistics to calculate the box plot, the median, the mean, the quartiles, the interquartile range, and everything outliers is handled by the geom underscore box plot function. We are not exactly like directly calculating any statistics such as the median, quartiles, and all. So geom underscore box plot does it for us under the hood. So this is how we basically call statistics within a geo. So this was a second example. Now, what if you want to calculate statistics separately? So we can also you do that using the statistics grammar in ggplot. So basically, we read some data, new data. By data is iris. So basically, this is the iris data set that we are familiar with. We have 5 columns: sepal length, sepal width, petal length, petal width, and the species of different flowers. Flowers. Now, basically, we are creating a plot, ggplot. We are giving the data, bar dot data. In aesthetics, we are saying plot species in the x-axis and petal length on the y-axis. Right. Then we are giving it a grammar of statistic. So stat underscore summary basically helps us calculate certain statistics such as, so if in this keyword fun dot data, we are giving it mean underscore SE. So what it will calculate is mean and standard error of the data. And in geometry, we are giving it bar. So it will basically plot a bar graph. Right. If we run this, we basically get a bar graph. We are getting the mean values for the petal length column across all different species. But note that we are not calling a geom object here. We are calling a statistic object, which basically calculates the statistics that we provide here, which is mean, and then plots it using another by calling the geom object bar. So we get a bar graph. Right. Yeah. Now we want to add another. So we want to add error bars basically. Right. So we have the mean here. Mean values are plotted here. We want to put the error bars. What is the standard deviation? Right. So we take the first bar plot that we have here, and we just add another statistics argument, statistics grammar, stat underscore summary. Now we want the function mean underscore SDL, which basically gives us the standard deviation multiplied by some value. So that value can be modified here. So function dot fun.args is equal to list mult is equal to 1. So basically by default it is multiplied by 2, but we want to multiply it by 1 because we just want one standard deviation, not two standard deviations. And the geometry will tell that ggplot we want to plot error bars based on these values, and width is basically what should be the width of the error bar. If I plot this, you see we have the bar graphs where the values of the bar are the mean, but the error bars are also there based on the statistics function that we just called. It basically calculates all that. So one thing we want to change is, so this graph does not look that great because these bars we don't want. We just want the bars above and not the ones inside the bar, the error bars. We don't want it to be inside the proper bar of the graph. So what we'll do here is we'll arrange the layers. So first we'll call ggplot. Anyways, we are providing the data and what to plot where, x-axis, y-axis. Then we'll call the error bar function so that it plots error bar first. And on top of that, we'll call the bar function so that it plots the bar function after that. If I run this, you see that the error bar was called first, so it was plotted first. Then on top of that, we plot the bar plot. So the bottom half of the error bar is not visible here. Okay. So this is the final bar plot. So basically it's the same thing. We provide bar dot data. We tell it X means species, Y is petal length. We first put the logic for the error bar. Then we put the summary statistics for the bar. We give the x-axis, we don't want any labels. We have all these three labels. We don't want this species written here. Y-axis, we want it to be called petal length. Y limit, we are changing from 0 to 8. And theme, we are changing. And the size of the axis and the text, we are changing. Right. Now we get a better plot. So that was all about uh, plotting with R, all kinds of data visualization that we have been taught in this week. Does anyone have any doubts? Okay. So, sir also talked about networks. So basically in biological system, we have a lot of different kinds of networks such as protein-protein networks or gene expression networks and so on, gene regulatory networks. So to represent networks visually or mathematically, we use graphs basically. So graphs are these kinds of things. So basically this thing here is called a node, and this thing here is called a edge. So edges basically connect nodes, and nodes are elements of the graph, right? So in when we are making a graph in biology, we can represent molecules or genes or disease or person or things, entities basically, like as nodes. And edges are basically connections between or relations between those entities. So things like physical association, proximity, similarity, functional similarity, regulation, expression, and so on will be uh, visualizing as edges. So in the top example here, we have a graph which has three nodes. So basically G1 is equal to, we write in curly brackets, n equal to 3 because the number of nodes is 3, e equal to 2 because the number of edges is 2. In the bottom here, we have another example of a graph. Here we have four nodes, 1, 2, 3, 4, and we have three edges. So this is how you represent a graph mathematically. Right. Graphs can be directed or undirected. So undirected graph means that there is just a edge between these two nodes. So let's say this is A and this is B and this is C. There's one edge going from A to C and going from C to A. So this is basically bidirectional. There's no direction here. There's a node connecting them. So for example, if you are making a graph of protein-protein interaction, we'll have an undirected graph because if protein A interacts with protein C, then by default protein C also interacts with protein A, right? We can also have directed graphs, which are basically graphs where there is some sense of directionality. So, for example, in signaling pathways or molecular signaling or gene regulated networks, we'll have directed graphs. So, for example, if A, B, and C are three different genes, and gene A activates gene C, and gene B also activates gene C, but gene C does not do anything to gene A or gene B, then we can use these arrows to say that gene A activates gene C and gene B activates gene C, and so on. So in this case, there is some direction. So if a gene is modifying the expression of another gene, we have a direction or an arrow from one gene to another. Similarly, for molecular signaling, we'll have molecules as nodes, and we'll have an arrow denoting what molecule is signaling what. We can have a lot of information in a graph visualized. So for example, we can change the shape, size, and color of nodes to represent different things. We can also change the shape, size, and color of different edges to denote different things. For example, let's say here we have some gene regulating network here. A is a gene that upregulates B. So that's why we have this arrow and this color. So this green color basically means that A is upregulating B. Red color here means that B is down regulating C. So the color here stands for up regulation or down regulation. Right. These colors in the nodes means that A and B might be genes that are, let's say, connected together or found together. And C might be a gene that is found somewhere else. Right. Or physically far away. The size basically tells how much it is expressed. So here A gene is B gene is expressed the most, then followed by A and followed by C, and so on. So we can have different sorts of information in different kinds of graph that is denoted by the shape, size, and color of nodes or edges in a graph. So we'll take a look at different graphs later and we'll see how this is implemented. So as an example, we have a graph here only. So basically, this is a protein-protein interaction graph. It's an undirected graph. So all the nodes here in these graphs are different proteins. Okay. And the edges basically mean that this protein is interacting with another protein. Okay. This is a very simple graph where we are the node size and the node color depends on the degree of the node. So the degree is basically how many edges a node has. So these nodes basically have a single edge. That's why they have smaller size and a different color. And this uh, node, which is a protein, OCT4 or something, which has, which is like a central protein which binds with a lot of other protein or interacts with a lot of other protein. So it has a bigger size and a different color. So it's easier to visualize and denote which proteins are more active or which proteins interact with other proteins more and so on. So this is all about visually representing a graph. Mathematically, if we were to represent a graph, we do that using something called an adjacency matrix. So basically, for example, if we have this graph here, this protein-protein interaction graph, we'll have a corresponding adjacency matrix where we'll have all the proteins lined in the rows, all the different proteins, and the same proteins also lined in the rows here, and the same proteins lined in the column also. So basically, this is the square matrix where the rows are these different proteins and the columns are also different proteins. Now, if there is a zero in a cell, it means that this protein is not connected to this protein by any edge. So basically, P1 is not connected to P1. If there's a 1, it means that P1 is connected to Pn minus 1. And here P2 is connected to Pn because there's a 1 here, and so on. So basically, 1 means there's an edge between these two nodes, and 0 means there's no edge between these two nodes. That is how you represent a matrix in a tabular form. Okay. So here we have an example of an undirected biological network. So this is the gene co-expression network. So basically, which genes are expressed together and which genes are not expressed together, kind of. So here, all these nodes are different genes. Okay, all these nodes are different genes. The node size again represents the degree. So basically, how many other nodes or how many other genes it is associated to. Okay. The node color basically represents the fold change. If the node color is red, that means the gene is upregulated. If the node color is green, it means the gene is downregulated. And the edges basically represent some value of co-expression. So if this gene is expressed, the edge means this gene also is somehow related to the expression of that gene. So we'll take an example to see how we can make a gene co-expression network from raw data. For example, if you have certain experiments you run to check the expression of four different genes, G1, G2, G3, G4. You see that in experiment one, all of them are expressed as one. In experiment two, there are different expression values. Three, four, there are different expression values. Okay, basically you're maybe adding some reagents, taking away something and repeating sets of experiments. Here in red, it is shown that gene 2 across the experiments, the expression decreases. In blue, G1 and G4 expression increases. And in black, G3 expression more or less remains constant across experiments. Right. So first step that you need to do to get a gene to build a gene co-expression network from this, you need to calculate the correlation or association between the genes. So we'll be calculating the Pearson correlation between the genes across experiment. So correlation of one gene with itself should be 1 because of course it's the same values across experiments. Okay. Now note that G1 and G4 are basically increasing across the experiments. So they should be correlated because as gene 1 is increasing across experiments, gene 4 is also increasing. So if we see the value of G1 and G4, the value is 0.97, which is quite high. For gene 2, again, gene 1 and gene 2, if we compare, gene 2 is decreasing across experiments, gene 1 is increasing across experiments. So like G1 versus G2, okay, there should be a minus here. Yeah. So basically, it's correlated. So, but as gene 1 is increasing, gene 2 is decreasing. So it's a negative correlation. And so on. We calculate the correlation for each of these genes and we get a matrix like this. Then we put some threshold. So these, when we are making a graph, basically we don't want edges from one gene to the same gene. So these red values will anyways set to 0 when we are making a adjacency matrix. Okay. Then we are setting a threshold as zero point 0.9. So if the correlation is greater than zero point 0.9 or less than minus 0.9, we basically put a edge there. Okay. So for example, here since the correlation, all the blue values, here the correlation is 0.99. So we put a edge there, 1 here. Here the correlation is less than 0.9. So we put a 0 here. Here again the correlation is greater than 0.9. So we put a 1 here and so on. Then we create a adjacency matrix. Now we can easily use this adjacency matrix to create a graph. We'll first have all the genes G1, G2, G4, G3. So G4 is colored red basically because it's decreasing across experiments. It's getting down regulated. G1, G2 are getting, sorry, this should be G2. This should be G4. Yeah. G2 is getting down regulated. G1 and G4 are getting up regulated. And G3 is black because it's not more or less changing. So now what we do, we look at the first row. We see that G1 has connections edges with G2 and G4. So we put two connections, one with G2, one with G4. Right. Then the second row we see G2 has connection with G1 and G4. So G2 already has a connection with G1. We just need to add this one. We'll add this. Then G3 has no connections with anything. And G4 again has connection with G1 and G2. G4 is already connected to G1 and G2. We don't need to worry about that. So this is how we create a gene co-expression network. The example that you see here is basically has done this thing for a large number of genes and across large number of experiments, right? Here again, we have an example of a directed biological network, which is a gene regulatory network in E. coli. So yeah, basically this is G2 and not G4, and this is G4. So G2 is down-regulated, so it is in red. G1 and G4 are up-regulated, so they are in blue, same color. Okay. So yeah, brown in this graph, it's a gene regulatory network in E. coli. So the nodes are gene. The brown nodes, basically these nodes here are basically genes that are regulated by other genes. Green nodes are basically transcription factors that are not regulated by anything else. And the red nodes that we have here are also transcription factors that basically control the expression of other brown genes, but they are in turn regulated by some green or some other red gene. So basically, these are transcription factors that are controlled by other transcription factors and they regulate the expression of another gene. And these arrows basically denote which gene is regulating which gene. So here, this green gene is regulating all these three brown genes, and here this one is regulating all these two, and so on. So this is an example of a directed biological network and how we show information in a directed biological network. Right. We can also represent networks in visually different ways so that it's easier for us to understand or get something from it. For example, on the left-hand side here, we have a gene co-expression network of flowering genes in Brassica rapa. Okay. The genes are basically arranged in circles based on the different flowering time pathways. So this is one pathway, and these are all the genes that are involved in this vernalization pathway. Okay. Then these are genes that are involved in light signaling, this circle here. This circle is genes that are involved in the development, and so on. So we have these different circles denoting different pathways, and then we can easily visualize what are the connections between these elements in a given circle and how these elements are connected to other elements across different circles. Okay. So it makes it like easier for us to understand in plots like this compared to just plotting everything randomly like we have here. If you make like separate clusters based on or circular clusters based on some sort of uh, variable, then that makes it easier to visualize. Another representation of network is also the Sarkos plot, which is basically a circular representation of uh, gene expression here. So on the left hand side, we have all the kinds of different cancers. On the right half, we have all the different genes, the expression of genes. And these connections basically tell you in which cancer, which type of gene is expressed more, or which gene is expressed more and which gene is expressed less. So green basically means upregulated or red means downregulated or something like that. Okay. So these are the different representations that we can use to show basically networks or visualize networks. For network visualization, you can basically use a program called Cytoscape. Or in R, if you want to do Circos plots that I showed here, the right-hand side, you can use the Circlize package in R. If you want to view or visualize graphs and incorporate multiple variables into like for example, change the node shape, node color, and everything, you can use according to different variables. You can use path view and SVG view R packages. And for doing quantitative analysis on graphs, you can use the iGraph. package, right? So we won't go into the details of these things. For now, we just have shown what is a graph, what is a network, and how we can visualize networks as graphs. So for this week, we have a few practice questions. Does anyone have any doubts? Okay. So the first question is, which of the following will you use to specify the name or label of the horizontal axis of a scatter plot created using R? So basically, to specify the label of the horizontal axis, which is the x-axis, we use the function called xlab. So this is the correct option here. Xlim basically determines the limit. Axis will basically tell you about axis, and CEX basically changes the size of the plot, the point of the size of the data point. The second question is, the first quartile and third quartile of data are 2 and 8 respectively. We represented this with a box plot. Which of the following points will be shown as an outlier in this box plot? So we know that Q1 is 2, Q3 is 8. Then we can calculate the interquartile range, which is nothing but Q3 minus Q1, which will be basically 8 minus 2, which is 6. So we want to know which of these points will be an outlier. So basically, when we have a box plot, okay, we have the median here, we have Q3 here, we have Q1 here, and these are the outliers. So we need to figure out what is the maximum of this data, maximum value. So the maximum is given as maximum is equal to Q3 plus 1.5 into IQR. So Q3 is basically 8 plus 1.5 times IQR is 6. We do 8 plus 9, which is 17. So the maximum value that we can represent in our box plot will be 17 here. This is 8, this is 2. If you want to calculate the minimum, it will be Q1 minus 1.5 times IQR. So basically 2 minus 9, which is minus 7. So this should be minus 7, right? So anything that is above 17 will be an outlier, and anything which is below minus 7 will also be an outlier, right? So we have options 5. 5 falls in the middle, so this is okay. 10 is also okay. 15 is also okay. 20 will be our outlier because it is greater than 17. Is that clear? Okay. Which of the following statements is true for a gene co-expression network? Two nodes are connected if their expressions are highly correlated. Two nodes are connected if one of them is a transcription factor. Each node represents a sample in a gene expression experiment. It is a directed network. We know that gene co-expression network is not a directed network. Okay. We know that each node will represent a gene and not an experiment. Two nodes are connected if one of them is transcription factor. This is also not true. The true statement is two nodes are connected if their expressions are highly correlated. When we looked at gene co-expression network, basically means that the nodes are gene and the connection is based on the fact that if these two genes are expressed together or not, right? So if their expressions are highly correlated, then these two nodes will be connected. So the answer here will be A. Okay, is that clear? Okay. What is P2 in the following R script? So P1 we have ggplot, data, aesthetics, x is equal to A, y is equal to B. P2 we have P1 plus geom underscore line. So P1 basically has data and aesthetics. So it tells ggplot what to plot and where to plot. How to plot it is basically given in P2, which is geom underscore line. So basically ggplot will plot a line with x-axis A, y-axis B from the data given data. So we'll read through the options. P2 is the line plot with A and B in the horizontal and vertical axis. P2 is an empty plot with A and B in horizontal and vertical axis. P2 is a scatter plot. P2 is an A versus B scatter plot with data points connected by a dotted line. Since we are not using geom dot point, this graph will not be a scatter plot. So option C and D are false. Since we are using geom underscore line and we have the data and the aesthetics, this will plot. It won't be an empty plot. So this option is also wrong. The correct option is basically this. So P2 is a line plot because we are using geom underscore line. And the x-axis, the horizontal axis is A. The vertical axis, y-axis is B. Horizontal, vertical. Okay. Vertical. Does anyone have any issues? Great. We have a data matrix with 20 rows and 40 columns. We want to create an image for this matrix where colors will represent numerical values of elements. What type of plot should we use? The answer here will be a heat map because that is basically the definition of a heat map. We have some rows, we have some columns, we have numerical values in the cell, and we want to represent it as colors. So this is basically a heat map where like darker color would mean that the value is high and lighter color would mean that the value is low. Right. What is the difference between plot 1 and plot 2 in the following code? So plot 1 is given as ggplot data aesthetics x equal to x data geom histogram bin width is 10. Plot 2 is basically the same thing, bin width is 100. So option A is the histogram in plot 2 is bigger than in plot 1. Since we are not putting any size things here, this is false. Both the things should come out to be the same size. The number of bins in histogram is more in plot 2 than in plot 1. This will be false because in the plot 2 we have bin width of 100. Okay, so let's say we are making on the x-axis we have from 0 to 500, and in the second plot what we are doing, plot 2, what we are doing, we are binning from 0 to 100, then 100 to 200, 200 to 300, 400 and 500. So we'll have 1, 2, 3, 4, 5 bins total. In P1, what we are doing, we are binning in 10. So 0 to 10 will be one bin, 10 to 20, 30, 40 and so on. We'll have more number of bins in P1. So the option third is number of bins in is more in plot 1 than plot 2. This should be correct. This is true. But we'll also check the last one. Both are histograms. But in plot 2, the data is smooth. This is also false because we are not using any geom underscore smooth function anywhere here. Is that clear? Okay. Which of the following functions does not plot raw data but plots the data statistics? Okay. So histogram basically plots statistics of data. It basically bins the data and calculates statistics and plots the distribution of the data. Geom underscore line basically plots a line. It does not calculate any statistic. Geom underscore point also just plots the points. And bar plot also basically you're giving it a value. It basically uses that value to plot bars. So all three of them, you plot the raw data, but geom underscore histogram basically plots data statistics. Okay. Which of the following functions will you use to change a data frame into a matrix? Cbind is to bind columns. Frame to matrix is also incorrect. Data dot matrix is the correct one. Reshape is also not. So the answer to this question is data dot matrix, and we provide it a data frame. It will give us a matrix of that data frame. Okay. The adjacency matrix of an undirected graph is always symmetric, true or false. Okay, so let's take an example. Let's say we have a graph here where we have three nodes, N1, N2, and N3, right? And these two nodes are connected, these two nodes are connected. It's undirected, so we don't have any arrows here. Let's write down the adjacency matrix for this. N1, N2, N3, N1, N2, N3. Right. So these diagonals will be zero because these nodes are not don't have any edges to itself. Then we see N1, N2, there is a node edge here, so this should be 1. N1, N3 also there's an edge, this should be 1. N2, N3 there's no edge, so this will be 0. Now note that whatever value will be here, N1, N2, will also be the value here. If it's 1, it's 1. If it's 0, it's 0. Because a node that goes from N1 to N2 also connects N2 to N1. Similarly, in this case, N3 and N1 will have the same value here, 1. In the third case, here, N2 and N3, N2 and N3, this will also have the same value, 0. Right. So we see that whatever values are on the upper right corner are also present in the lower right corner. And the diagonal, all the elements on the diagonal are 0. So if we transpose this matrix, we'll basically get the same matrix. And since this is the adjacency matrix, it's always a square matrix because on the columns and rows, we have the same things, the nodes. So this is basically a square symmetric matrix if the graph is undirected. The answer here will be true. Is that clear? Okay, so that's it for today's class. Does anyone have any doubts? Okay, yeah. Uh, okay, so we'll stop the session. Yeah, that volcano plot thing we'll look at now. I'll just stop recording.